minimum absolute sum difference. So I've solved this problem yesterday, so I think today I can still solve it. Let me first explain the problem. So we are given two positive integer arrays, nums1 and nums2, both of less n, so they have the same length. The absolute sum difference of arrays nums1 and num2 is defined as the sum of absolute of nums1I minus nums2I, and for each I inside the range of the array. Yeah, so it is a zero indexed. Yeah. You can replace at most one element of nums1, so we can only replace element in nums1 and at most only one element in nums1, or we don't need to replace any element. Yeah. And we wanted to, we can replace this any element in nums1 with any other element in nums1. So for example, in this example, we can replace this 7 with 1 or 5, but we don't need to replace with itself because it means we didn't do anything. We need to return the minimum absolute sum difference after replacing at most one element in the array nums1. At most, we replace one element. For example, we're gonna replace 7 to 1 or to 5. So the final result gonna be 3. You can check, this line or this line. But definitely this gonna be the minimum value. And the final result would be 10 modular 10 to the power of 9 plus 7. So we should know about this. So this is the absolute definition. And the length of nums1 and nums2 is 10 to the power of 5. So this means we cannot solve it by brute force, by n squared. We have to solve it like O(n) or n log n. So this problem seems to me it is a n log n time complexity. So let me first analyze the problem. I'm gonna use the third example to analyze the problem. So if I have two arrays, so this is nums1 and this is nums2. I just want to make an alignment. And you can see it clearly what it looks like. If we are going to check the absolute difference of each element, so absolute of 1 minus 9, it is 8. And what about the second? 10 minus 3, it is 7. And then it's gonna be 1. 4 minus 1 gonna be 3. 2 minus 7 gonna be 5. And the last one, 7 minus 4, gonna be 3. So this is the absolute value. If we don't need to replace anything, so this is gonna be our result. So currently we can replace one element in nums1, but we need to decide which element we want to replace. Let's check the answer. So the answer from here is gonna be the first element. We're gonna replace 1 with 10. We just need to analyze why it is this element. If you find a solution of this one, normally you can solve it. So we want to change this 1 to 10. But why we can do that? Currently, as you can see that the difference of 9 minus 1 or 1 minus 9, it is 8. But if we change this number 1 to 10, what is it gonna be? So currently the difference will be 1 because 10 minus 9, absolute of 10 minus 9, it is 1. So what is this difference, 8 minus 1? It is 7. Why we need to analyze like that? Because we want to find the maximum difference. 8 minus 1, it is 7. If it is in other places, definitely it is no bigger than 7. If we find the maximum difference, normally this is gonna be our result. So the final result would be these numbers plus the 7. Why? Because as you can see before, so it is 8. Now after replace 1 with 10, so the difference is 1. So this means our result, this means this element reduced by 7. So the final result should also be reduced by 7. Because of one element and because it is the sum of all elements. So the final result would also be 7. If we use this one, so the sum of all those values would be like 27. 27 minus 7, it would be 20, and this is gonna be our result. If you don't believe it, let's just try another number. So for example, we want to let me make the alignment, make it better for the alignment. Yeah. I just wanted to try another example to explain it. Yeah. So I think this alignment is okay. So maybe you don't believe that. So what about we're gonna replace 2? Maybe we're gonna replace 2 with 7. Yeah, can we do that? Yes. So here is still 1, and here this 2 gonna be 7. Yeah, but what is the difference? 7 minus 7 is 0, right? But before that it is 2. 7 minus 2 it is 5. So 5 minus 0, what is the result? So yeah, it is 5 minus 0, it is 5. Yeah, but what we want to find the maximum difference, it is 7. But here is 5, it means it is no better than the first one. Yeah, so we want to always find the maximum difference, which is 7. But how can we find this 7? We can use binary search. Why? Yeah, because for each of the elements inside nums 2, so for example this is 9, we're going to find the closest element to this 9. So what is the closest element to 9? It is 10, right? Yeah, as you can see, it is 10, because 10 minus 9, it is 1. You cannot find any other element which is close to 9, better than 10. Yeah, maybe 7, but it is 2. But you should choose this 10 if it is the first element. Yeah. So this means for the first element in nums 2, this 9, you can change it to the closest element. Yeah, you're gonna try if this is better or not. Yeah. So if you try this 10, so the result gonna be 1, because 10 minus 9 it is 1. But before 1 minus 9, the absolute of 1 minus 9, it is 8. Yeah. So what is the difference of 8 minus 1? So it is 7. So actually we just wanted to calculate this 7. We need to find this 7, and then the sum of nums 2 minus this 7 gonna be the final result. Yeah. Similarly for other elements, we have to try one by one, but this is gonna be n log n time, because we're gonna loop through nums 2 for each of the elements, and then we're gonna use the binary search to check in nums 1, because we want to find the closest element, and this nums 1 can be sorted. After sorting, it's gonna be log n time. So after sorting, it's like 1, 2, 4, 4, 7, and 10. Yeah. So we want to find 9, it is closest to 10, and we're gonna find 3, it is close to 2 and 4, and we're gonna find 5, which is close to 4. Yeah. And we're gonna find one by one. For 1, we're gonna find this one, it is closest. And for 7, we're gonna find this. We're gonna find this 7, it's gonna be the closest. For this 4, we're gonna find this 4, it is the closest. Yeah. Even we find the closest, we should check the absolute value, the final result. I mean, this is 7. This 7 would be the maximum. The final result would be the sum of nums 2 minus this 7, because it can always be reduced to a smaller value. Yeah. If you didn't get some result like 7 or other values, maybe it is 0, you didn't get any result. So it means you don't need to change any element in nums 1. Yeah. I hope you understand the solution. So for me, my intuition is that I find a solution to use the binary search, and then I'm gonna use the binary search to solve it. Yeah. Now let me just start coding. I'm not sure if I can solve it today. Normally for yesterday I just solve it like in half an hour. So today I just wanted to try to use solve it quickly. Yeah, now let me just start coding. So I'm gonna use a zip. So for I, let me use n1, n2, or ab. Yeah, let me just use ab. So yeah, for I, ab in enumerate, I'm gonna enumerate nums 1 and nums 2, and enumerate would be a zip. I'm gonna zip it inside. So nums 1 and nums 2. Yeah, and I'm gonna prepare a final result and the maximum, current maximum value, because the final value would be the result minus this maximum. And I'm gonna also prepare a mod because the final result would be modular this value. So the result would be 0 and maximum would be also 0 and the mod would be 10 to the power of 9 plus 7. So this is my variables. Now I can use the binary search, but before that I need to sort the array of nums1. I need to sort it. So nums1 should equal. I gonna do some tricks. Normally I would like to do this kind of tricks because I can avoid a lot of edge cases for binary search and plus infinity. And you're gonna understand why I'm gonna do that. But I'll always do this. I'm gonna explain this later. Yeah, if you are familiar with binary search, maybe you can think about this kind of tricks to solve a binary search problem. Otherwise, you have to check all the conditions. It's gonna be difficult to use binary search. I'm gonna explain this later. So after preparation of nums1, I'm gonna sort it. So nums1.sort. Yeah. So currently nums1 has already been sorted. So this means I can use a binary search to search which value is close to nums2. Yeah. So here nums2 is this b. B represents element in nums2. So I'm gonna use index j. So j should be equal to bisect. I'm gonna use the bisect left. I'm gonna explain this bisect left later. I'm gonna use the examples to explain it. Yeah. So for the bisect left, it is nums1. And in nums1, I'm gonna search the value of this b. Yeah. So let me check the first value. For example, this is 175. Yeah, let me just put 175. After sorting, it's gonna be the minus infinity, 1, 5, 7, and positive infinity. It's gonna be like this. This is for nums1 in example of nums1. And so for this j is bisect left. I'm gonna use a binary search to search this element b. So currently b is 2, right? Yeah. So for this 2, you should know about that. The index should be, this j should be 2, right? Yeah. So I want to get the let me think about it. I want to get the most closed element to this b, to this 2. Yeah, so it should be 1. But how can I get this 1? Yeah. So yeah, here I'm gonna use this. Yeah, let me check. I'm gonna use the most closed element. So I'm gonna use a minimum value. It's gonna be the minimum of 2 values, which is close to this number 2. Yeah, because first element. So this 2 would be close to this. Yeah, if I use a bisect left, the 2 would be here because 2 is more than 1. If it is more than or equal to this number, so it's gonna be insert at this position. If it is more than 1, it's gonna be insert here. So if this is 2, it's gonna be inserted at index 1. Yeah, but here this is 1 and my b, this number, is 2, so it's gonna be insert at this position. So I can get the minimum value between this b and 1 and 5. Yeah. So maybe this is not 5, maybe it is 3, or maybe this is 2.5. So the closest number would always be 1 or 5. Yeah, you have to understand something like that. Otherwise, you cannot solve the problem using binary search. Yeah, bisect left. So I'm gonna check the closest value. It's gonna be minus nums1 with j minus 1. So because this b is number 2 and j minus 1, j is 2, j minus 1, it is 1. It is this value 1. Yeah. Or it can be another value. It's gonna be nums1, j, and minus b. Yeah. And this is gonna be 5 minus 2. So this is why I prepared this kind of infinity, because this is gonna be easier for me to solve the problem. Yeah. So currently this number is 2. So for example, if this number is 1, yeah, if we were to use binary search to find this 1, so for the index it would be 1. Yeah. So it's gonna be the minimum of 1 minus infinity, it's gonna be infinity, and 1 minus 1 it is 0. So for the final minimum result, gonna be 0. Yeah. And my maximum value would be the maximum of this max with the minimum value. Yeah, so for here it is a little bit confusing. You should understand that. So from here, I would always find the closest value. It's gonna be the minimum. But for the maximum value, it's gonna be the yeah. Let me think about it. Yeah, let me just think about it. So for the maximum value here, so yeah, let me just use this example. Maybe this example is better to explain. Yeah. So for example, for this 9, I'm gonna find a value of 10. 10 is the closest. So I got a minimum of 1, and it should be 8 minus 1. Yeah, I need to find this 8. So the 8 would be this 8 is yeah. So here I need to also prepare the result. Result should be plus absolute of each of the value. Yeah, I forgot about that, but I needed to use that. So b minus a. Yeah. So here similarly, I needed to use the absolute of b minus a or a minus b. Yeah, minus this value. So before this is for the first element, it is 8. 8 minus 1, it is 7. So the final result would be the result minus the maximum modular the mod. Yeah, I'm not sure if you totally understand it or not, but the basic idea is binary search. Here I just use some tricks for the binary search. It means I don't need to check the edge cases. And for this one, it's just for the result. For each of the elements, I need to plus, like 9 minus 1, I need to plus all the values. So here, I've got the result. But I need to use this result minus this maximum value. If I didn't find it, maybe it is 0, so it's going to be result. If this maximum value, maybe I've already found the maximum, maybe this 7 is the maximum, I'm going to just minus this 7. You can just use this example to try to understand my solution. I hope you can understand it. Now let me just run it to check if everything works. Something wrong. Yeah, this is something wrong. Yeah, let me just check what is wrong with it. Yeah, let me first check this result. Here I'm gonna prepare the result and maximum. Maybe something wrong with my maximum value. Yeah, I've always got an infinity. This is definitely wrong. Yeah. I should not use this kind of infinity. Yes, because yeah, this nums1 should not be nums1. Otherwise, I would make it confused. Yeah, because for nums1, it should be the length of 3, and also for nums2, the length should be 3 for the first example. But here, I've plus minus infinity and positive infinity. I make it length to 5. Definitely, it is wrong. So I should not use nums1. I should use nums should equal to this kind of a value, and then I'm gonna use the binary search to just search the nums. I think you should understand that, because it is currently not nums1. Yeah, and here gonna be nums sort. Yeah, I have to prepare a new nums. It is a copy of nums1, but with a padding of infinity and negative infinity, and with that we can solve it easily. Now let me just run it. The index is out of the range. Yeah, this is also not expected. This is nums1. Oh, it is not nums1. Yeah, because I've already changed it to nums. Yeah, because currently we have to use nums, not nums1. Now, as you can see, it works. So the basic idea is you should try this example. And after adding this minus infinity and positive infinity, it's gonna make the index just inside the range. It's gonna never be out of the range. And it's gonna be easier to use this kind of a formula to get the result. This is the why we're gonna use some tricks. Yeah, I've used this negative infinity and positive infinity in a lot of binary search problems. I hope you can also use this kind of tricks to solve the binary search problem easily. Now let me just run it to check if it works. Yeah, I should delete the print. Yeah, because it will influence my time. Yeah, so after deleting the print, let me submit it again. Currently it is 23. Now let me submit it again. I think it should be increased. Yeah, because the print takes time and memory. Now as you can see, it is 57% of all submissions. And the time complexity is here. It is n log n time. And also from here, it is n log n time. So the final complexity is n log n. Thank you for watching. See you next time.